Hello, my name is Milana Lima dos Santos. I'm assistant professor at Universidade de São Paulo in Brazil, and I will present our experience about using Mathematica dynamic functionalities to provide the students a visual understanding about electrical concepts and electrical drives for students that are electrical and non-electrical engineering students. Hello everybody. I apologize for my poor English. It's my first time here in the conference, so I hope that the message is clear. My name is Milana. I'm assistant professor at Universidade de São Paulo in Brazil. And we are presenting here our experience in using dynamic functionality of Mathematica to provide the students a visual understanding, because we are responsible, me and my colleagues in our department, can you hear me? I don't know. Are responsible for courses that about basic electricity that are offered to students that are electrical and non-electrical engineering students. Well, the Politecnico School is part of the Universidade de São Paulo in Brazil. It's older than the USP. Politecnico School was created in 1893, and now it has 125 years. And USP is the most important university in Brazil. It was created in 1934. We have almost 5,000 students enrolled for 17 engineering courses. And my department in Politecnico School is responsible for some of these areas in electrical engineering, about automation, power electronics, fundamentals of power systems, and disciplines about energy and basic electricity here are offered to most of the 17 courses. And it involves a lot of professors like me. Well, I'm using Mathematica for only 3 years. So I apologize because my code is not as clean, so maybe it was effective. This photo is not mine. I use it from Wikipedia, but it is here to show that we have a few hours to show students that are from production engineering and chemical engineering how this works, how electric motors works. So we use Mathematica for that. It's one of the topics that we try to teach them. So the first topic we covered about motors is how it can spin. So we had 3 hours for the students to learn how it works and to manage to start a real motor. They are presented to a 3-phase motor, electric motor, and they need to make it rotate without with the right connections for a 3-phase. So first of all, we try to use manipulate and get the images from this manipulate to a real presentation. So the code is here, but it's not so clean because I'm not a real programmer. I'm not a computation engineer. So maybe if my code is not so neat, but I could manage to do that. So instead of using a board and a chalk, we prefer to make it run. So in this picture, we have a coil in which a current is present and a magnetic field called B in black. So the interaction between the current and the magnetic field generates two forces that makes the coil to spin. And all these images are created using Manipulate and Mathematica. So we can collect all this to a presentation that is not made with Mathematica because I'm alone in my department using it instead. I hope I could spread the news. But we use LaTeX to build presentations, so you can easily connect maybe 34, maybe 35, 36 images of them. And so we can use a feature for LaTeX that is animate. So we can use it to create a PDF that students can play forward and in the reverse, so they can believe that this can happen. And then for a DC machine, when it almost gets its equilibrium point, a commutator that is draw here in gray. It was kind of difficult to make this using 3D because it's difficult to draw a part of a cylinder using this function, but I managed to make it. And then after the equilibrium point, inertia keeps it running, and so the commutator makes the coil touch the source in the opposite polarity, so current is reversed. So coil continues to rotate. Then we have similar to AC machines, alternate current machines. So the field, and this way the field, it's not constant, it managed to rotate, so forces are rotating too, so the machine keeps running. One question students made is how this field is rotating. So I prepare some manipulate based on drawings that our colleagues draw. They draw maybe 5 or 6 drawings by hand. So I managed to automate this. So students, they told me that now they believe that the magnetic field in the center of the machine is running. Because here we have 3 currents, the three-phase current, one in red, one in blue, 120 degrees delayed, and another one in green. These currents are put in this motor in view from the front side. So current gets inside the screen in this position, and inside the screen this position, and outside outside from this position and inside from that position. So they generate 3 magnetic fields in red, blue, and green, and the resulting field, it's this gray. So when the time runs, the current here changes, and so the magnetic field here. But the sum is constant with different angle. So we save a lot of minutes drawings in the board showing this. And so the students can see this in Rome before and after the classes. And the students are very excited about how easy it is to do this code. Some of them asked me, so I show the code, and if they want to improve it, it's free for them. And so this is the result from the latest. So I only put it in LaTeX, this these buttons here are native from Beamer package, animate from Beamer package. Another concept that we use to make manipulate too is a very frequent question is about why do we need to correct power factor for alternate current circuits. When we use circuits that are not exactly modeling as a resistive one, when we have some part of inductive and capacitive elements, there are kind of displacement between current and voltage curves. As we are interested in not in voltage or current, we are interested in power, power that makes the world run. So you are interested in the product, in instantaneous product of these curves, the voltage and the current. And if they are displaced, the product, it's not only positive. There are parts that are negative. So it is kind of less efficient because sometimes you give power, sometimes you get power. So in the ideal world, we have this kind of curve. This kind of curves with about voltage and current in phase. So how we could correct the circuit to get the right, how can I scroll this? Okay, to get it. We have to sum, if we had a current that is lagging from the current that is lagging from the voltage, the peak occurs after the peak of voltage. If we sum some current that is leading, the peak occurs before the peak of the voltage, we can get a curve that is less displaced. So to calculate what is the exact curve, the exact current that we must sum, or the exact capacitor that we have that we need to add, we need to show students that we have the best way is to represent sinusoidal curves with phasors that can be shown in this animation that we've done with Mathematica too. If we see the balls in the right side of this plot, let's stop. The balls in the right side of this plot, it goes together with the other plot with time. So we can represent all these curves in sinusoidal curves with vectors that are rotating. And if we get the point where the time is 0 or a multiple of periods, we can use these vectors that we call phasors to do all our calculations. You can sum these phasors, and the sum is equivalent to sum these two currents. It's the first step that students should be able to correctly calculate the capacitors. And then they are able to see what happens when we add the correct capacitor to the circuit. Here we had a motor here that is part resistive and part inductive. And so the current that the voltage here needs to supply, it's 82 amperes. If we add a capacitor to the circuit, some of the current is provided by this capacitor, and then the source only has to provide 77 amperes of current. So the circuit gets more efficient. And the student can see what happens when we add more and more capacitor, and then the point where we add too much capacitor. So the current begins to increase again. So this is to add to our LaTeX presentation, so students can experiment it at home. And even they can see if the calculations are correct. Well, the story of my experience using Mathematica begins in 2015, 3 years ago. So I started to use it by myself. I was very interested about the visual results and the dynamic features of Mathematica, about manipulation. So I went to a Brazilian conference. Here, I don't know in each line. I went to a Brazilian conference. And so I started to change experience about it. I read the book from Stephen Wolfram, and I used a very known internet forum. So it helped me to do a poor coding, but that it works. The next one, it's a challenge for me because I am a lab professor. So this is our lab kit that students use, students from chemical engineering, production engineering. So these are some relays that are used to here we connect some resistors or motors. So students need to do the correct connections. So when they press this button, for example, a motor has to be started and keep running. And then when they press the off button, they have to stop the motor. And for example, they have to, after 10 seconds, the motor is running, another motor has to be started too. So how they could do this using this kit. So I wondered if it's possible to do it using Mathematica, how students could simulate it at home, or study for the exam, for example. So I managed to do it. It's quite slow, but I don't know any other programming language that I could use to do that. So in this screen, it's an edit screen. I'm sorry, it's in Portuguese. No? I could not translate it to English. So here, students can make its project. So we have a button here, an on button, an off button, a fuse to protect the circuit. And here is the coil. And the coil here, C1, has 3 contacts here. And if they are closed, a load is turned on. Student can change some of the position. I'm afraid of doing that because of the touchpad. I don't have the right precision, but it can, for example, delete this contact to see if it works or not. This is, I get here some 4 predefined circuits. Then you can use it, and you have to, you can create a new circuit too. And then when I go to operation screen, this circuit now may be operated. And this calculation is done with graph functions. So I use the graph functions, and I change it a lot about its appearance. So the labels are changed for these drawings, so the drawing is not so good. And the colors here are calculated using highlight function for graph functions. So I did it maybe 1 year ago, but there's something about calculating the path and highlighting the path. If it's okay, this coil will be turned on. So I press the on button, and then it works. And when I wanted to stop the motor, I use this button, the off button. If I use another circuit, it takes much longer to work. This is okay. It's a more complicated circuit because I had 2 coils and a timer, a timed coil. You get some time here. You can change the time, and then you may operate it. It takes a little bit longer. And then I can operate the system. And then it starts counting the time when it gets 10. So this contact will be closed, and the second load will be turned on. So I can turn it off. Well, the following notebooks was made with my undergrad students. The first I will show you is made with Marina Paulillo, that graduated 2 years ago. And then she wanted to do some manipulate things about power systems. This is specifically for electrical engineering students, because we deal with 3-phase circuits that are unbalanced. When the 3-phase are balanced, we have this kind of thing. 3 currents have the same magnitude, and the phases difference is 120 degrees. But when they are not balanced, we have a different amplitudes or different phase angles. So the first step to understand this kind of circuits is to separate it as a sum of 3 well-behaved circuits. One with this difference, another with the same differences with 2 phases switched, and one with 3 voltages or currents exactly equal. So we use a locator and some matricial operations to show how this could work. So instead of using calculators, you can see how it works. Another 2 works from another work from Marina is, I'm sorry, I don't know what's happening here, but let me see if it works. Okay, it works. As all of these notebooks were made in different times with different variables from different persons, maybe they have problems to running together in the same notebook. So in this notebook, we show how to calculate short circuits for 3-phase circuits, and with different kinds of transformers, for example. If we had grounding in one of these transformers, current may flow through ground. So if we have a ground circuit, a short circuit, there will be current. If there is no grounding, so part of the circuit it's open, so part of the current will not exist. So we can choose here if we get or not grounding. In this case, for example, this case is okay, but if we have short circuit in this point here, the current has no path to exist. So the current here in this table here is 0. But if I put grounding in this path, so current can exist, and it's stated here in this table. And I have a few seconds, but I want to show two works for my two students. One of them is Fernando, and he managed to do a notebook talking about a wind generator and turbines, but he wanted to do it without using manipulate, because he wanted to explore Mathematica and to see if it's possible to switch between different screens, only clicking on them. So he managed to do that. So here we had a curve of torque in the generator. So if you wanted to see the curve for power in more detail, only you have to click here. Oh. And so the curve is shown with more zoom. And also for this screen too. So we have to explore it. It was a great job that Fernando did. And another one, the last one, as my time is over, it was the last, but it was the first student that worked with Mathematica with me. We did it together with another professor, Professor Silvio, and the students was Vinicius. Oh my God. It's quite heavy. We have here a manipulate with 8 tabs that talks about how we can select electrical motors based on some desired features. For example, what kind of load we have to move. If we had a load with more torque, we have here. So this motor, it's not suitable because in the beginning of rotation, the torque is not enough to move the load. So if we use a different starting method, for example, this kind here, I'm not able yet to push it, but maybe we could do it with a slower load. So a student or any user can can choose different parameters of the motor using this notebook that Vinicius created. Thank you all for coming, and if you have any questions, I'm sorry, I am a little bit late.